Questions about entering PDEs? Is it clear so far? Yes.
So if you wanted an equation with like a fourth order derivative, is the weak form the only option you have because the template doesn't have higher order derivatives?
I will let you think about it. How can you do it? So let's say you have how do you solve, for example, if you have a higher order differential equation, say in dynamics?
Or do you make like, I mean, you could reduce it down to the systems of lower order equations.
So that's how
you do it.
Yeah. So before you enter it, you have to reduce it to a system. Okay, that was a good question. For some of these equations where we know people will have higher order equations, in our own, we have pre-implemented this. For example, in structural mechanics for membranes, you have like the biharmonic equation. And there we have already taken care of this. But the only thing you have to be careful when you are specifying this is the discretization you are using, right? Because let's say you had a fourth order, let's even talk about the second order equation. So you have a second order equation that, let's say in space you had in 1D, say d squared u over dx squared, but you decided to introduce an auxiliary variable w such that w is equal to du over dx. Then in your equation, instead of this, you're going to write dw over dx is going to be whatever originally you had, and then you're going to have du over dx is equal to, this is actually not anything, this is w itself, right? Now, the question is, if you went with this, and if you picked a certain interpolation function, right, for the finite element method, you are picking low order polynomials, right, which locally is low order polynomials and continuously stitched together to get your global solution. If you picked a second order polynomial for u, then w is going to be a first order polynomial, right? Or if u was twice differentiable, you are only going to expect one-time differentiability from this. But then when you did this, and you could inadvertently make w and u to be of the same order. But in general, they are not, right? And that choice of how you pick the order of interpolation, especially for mixed problems, is an important topic in finite element analysis. You probably have, guys discuss inf subconditions or something like that in finite element analysis. There are basically existence, uniqueness, stability issues that you might run into numerically when you use a mixed problem. So you are right in terms of splitting, but make sure that you are using the right approximation spaces for the new auxiliary variable you introduced. Yeah. Okay, yes?
Can you break your user-defined into stages? Like when we saw initially, you can solve in a stage, then you take your solution to another stage and solve. Can you do that with user-defined function?
Yes.
Then when you do that, because in the user-defined function, you define what to do and everything. How do you call a value from the previous stage?
Okay, so this is when you have a one-way coupled problem, is it? Or if I write it, let me see if I understood your question correctly. So you're saying maybe you had, say, a problem. C1. U, let me ignore other terms, is equal to some function f, but then I'm solving for another equation, let's say dw over d plus minus c2 w is equal to some function of u. So these equations are coupled, but they are only one-way coupled, right? In that, in here, you don't have any term containing W. But in here, you have a term containing U. So you could first solve just this one on its own. Then, next time, when you are solving this, you want to say, I want to use the solution for U in this equation. Is that what you wanted to do?
Yes.
Okay. So if that is what you want to do, say in here, the first thing is you can add a new equation, like a new physics. So I can come to physics, and then I can say add physics, do the same thing of going to mathematics, PD, let's say coefficient form. This time it's C. I will add that. Now here it gives the name C2. You can change the name. Let's say the other one is already, instead of C, let me actually rename it. Okay, that's U. And here, I want to name this W, right? The dependent variable is W. Now, if you come to here in the equation, now you have a template in terms of W, right? Now, if you want to enter, you have already entered this equation. You want to enter this. In that template, EA is going to be 0. DA is going to be 1, right, for the W equation. C is going to be some value. The only thing is, I'm going to have this source term, which should contain U, right? And in there, come to the source term. Here, let's say it was U squared, right? Then just type U squared. And that's it. So in console, actually, this is the way to make your own physics coupling. If two physics are coupled, the only thing you have to know is which term is going to contain something in terms of the other, and just type that in. And now the catch is here in the solver, it's going to want to solve both of them together, and that is, we do this for the sake of robustness, because possibly there is a two-way coupling and you need to solve it together. But now you, as an analyst, know from your equations that there is only a one-way coupling. Then that one-way coupling, you can enforce it. And the way to enforce it is here in the study, in the step, add a new study. Let's say I add a new step. So now I have two steps. But then in the first step, I just need to solve for that one. And in the second one, I need to keep only that one. So now what it will do is it will solve the first physics, and then there is a trickle-down mechanism. So you have to order these choices properly so that the first one doesn't need data from any other equation, and then in the second ones you can just use it. So the principle is that in console, any place where you could have typed a number, you could type a function, you could type an expression of another unknown, and that is how you actually make custom coupling. Does that address your question? Yeah. Okay. Other questions? Yes.
You don't have to make sure that for that second study that it's dependent on the first study. It'll just already know that.
Yeah, but sometimes that may not be the case. In this case, if you put them under the same study, it will just know that to get them from above. But sometimes, but then if I'm solving this, I'm solving both of them together, right? So sometimes you might be in a situation where you solve the first problem and you know you are not going to change it, and you just now want to tweak your second equation. So you don't want to be solving both of them together in two steps because the first one is dead. You don't want to deal with it, right? In a situation like that, instead of adding a new step, let me delete this, add a completely new study. And let me add a new study, add study stationary. See the difference? Earlier I had two steps within the same study, but now I have completely different studies. Here it doesn't know. It doesn't know where to get it from. Now in that case, let's say I only keep this. You see these values of dependent variables? If I expand that section, there is values of dependent variables solved for and values of dependent variables not solved for. Now at this point, the solution from above is something I'm not solving for anymore. I will just be using it as a parameter. So here you come and say you are user controlled. You're getting it from a solution from the first solution. So now you are indicating yourself. That answer?
Yep.
Okay. Other questions? So now let's move on to the other topics. Ordinary differential equations and differential algebraic equations. COMSOL doesn't make a distinction between ordinary differential equations and differential algebraic equations. If it doesn't see any derivative in your equation, it just deals with it as an algebraic equation. And if it sees a derivative, it deals with it as a differential equation. Now, when we mean ODEs, I want to make it really clear that we actually just mean initial value problems. So if you compare those two equations, they're really the same, right? The first one is in time, the second one is in space. Strictly speaking, mathematically, right, they are both ordinary differential equations. But in numerical analysis, they are treated differently, right? For example, if you're using the finite element method, the special derivatives, you're going to, the special one, you're going to take care of it by the finite element shape functions. Whereas for the time derivative, you're going to have a time integration scheme, something like a backward Euler or a higher order version of that. So space and time are dealt with differently. And because of that, when we mean initial value problem, when we mean ODEs, we just mean initial value problems, where there is no special derivative. If there is any special derivative, even if you don't have time derivatives, you have to use the PDE interfaces. Is the distinction clear? So you also need, for example, if you're solving the first equation is mostly like a particle dynamics equation where you would want to specify both the initial location and the initial velocity. Whereas the second one is more or less like an equilibrium problem in 1D where you want to specify boundary conditions at the two ends. So that is like a 2-point boundary value problem, whereas the other one is an initial value problem where you specify two initial conditions at one point. So they are different. So when we mean ODEs, in the context of COMSOL, we mean initial value problems. So between initial value problems and algebraic problems, there is no distinction. You can also have differential algebraic equations, right? You can have ordinary differential equations between which there is an algebraic constraint. And this can be global or lumped. What I mean by global is you have just one equation, whereas I mean global or domain or distributed. What I mean by domain is when you can have equations different ODEs every different place. That will become clearer when I get to an example.